एंजॉय नहीं कर सकता,
Hello.
रंग नहीं लगा सकता है, बोल ना,
Hello.
तो कपड़ा नहीं फाड़ सकता है वो।
Yeah. So good evening. I'm Devmala Roy. So I'm your TA for this live session. So start now. It's already 7:08, so I should start. So can you see my screen?
Yes, sir.
Okay. So today we will be doing this assignment one. So assignment one is I think based on your week one lectures.
साउंड कम करना।
Okay.
कितना बच्चे को क्या
Assignment 2, sir.
Mhm.
Assignment
So
2
assignment two we will be doing next week. Okay.
next week.
Yeah. Hmm.
Okay.
This week is assignment one. All right. So this is question number one. So let's start with the questions only. So the questions are ordered in such a way that it gives you an idea about what this course like will mainly deal with. It gives you an introduction to the fluid mechanics and when what is applicable and the main things that we will be dealing with. So first thing here is basically
Hello, sir.
yeah.
Live session video uploaded YouTube.
Yes, I think the link will be shared with you.
Share with me. Okay.
Yeah, the link will be shared with you. Have you received the link for the last week's video? I guess you should have received the link to the last video. Okay. So you can like I think post it in the forum if you have not received. Uh, the link should be shared with you. I'm not part of that forum. I'm only here for the live sessions. So okay. So we'll start with the first question. So uh, here, what we are really means this what this question is mostly about is the length scale in which we are studying the fluid. So there is a very important assumption that we use many a times. So yeah, this is the continuum assumption. So have you heard about this continuum assumption? I guess you would have studied it, right?
Yes, sir.
So can you just explain what do you mean by a continuum?
Sir, in continuum assumption, fluid is regarded as a continuous medium,
Yes.
disregarding of the discontinuity.
Yes, sure. Hmm. So, fluid, as we know, all materials are composed of some smaller elements like molecules. Hmm. So, all fluids are also consist of molecules. So, they should be regarded as a particles. But that makes us very tedious to predict its nature, what it will do. Because if we like consider fluid as individual particles, we have to solve the equations of motion for every particle. For every particle, we will need to solve the Newton's second law of motion and find out its velocity and find out its position. And that will be very tedious, very hard to do. Even for a supercomputer, it will be extremely difficult to do like beyond some maybe nanoseconds or for a very small scale. So what we do is basically we take a group of um, uh, like we take a control volume. So we take a volume and we see that there are a huge number of particles here. Even if this volume is extremely small, there are a huge number of fluid particles here. And if we take a statistical average, like for example, what is the mass of this? Hmm, what is the mass of this particular volume? So let me go to the next. Yeah, this I have left empty for this discussion itself. So suppose we take a box. Now let's say there are only two molecules here. So two atoms here. So one may go out, one may like come in, maybe a third can join at some point of time. Hmm. So the number of molecules will keep on changing because there is motion in the fluid, and thus, if I try to calculate density here, hmm, so this density will also keep on changing. So this volume is fixed, hmm, but I need to for calculating my density, I need mass. So this the number of molecules here is constantly changing because the volume is so small. If I increase this volume, so what I'm doing is basically increasing this volume. If I increase this volume, more number of uh, fluid molecules will be inside. So, for example, I have increased my volume such that there are about 100 molecules here. So now also due to the its motion and due to thermal fluctuations or fluid motions in general, molecules will be constantly leaving this volume and also constantly coming inside. So this 100 may vary, but it will vary up to let's say like 105 or to 95. Hmm. So we'll still get a varying density. Hmm. The average of this density will start converging to a particular number, but it will still vary a lot. So if I increase my volume, hmm, if I increase my volume, for example, like earlier at the first when I was talking like one or two molecules, maybe the length scale of this was in angstroms. Some angstroms of 2 or 3 angstrom may have been the length scale of this box. So it is like 3 angstrom by 3 angstrom by 3 angstrom, a cube is small cube is there. Now for 100, maybe I'm talking about few nanometers. Hmm. So suppose like 3 or 4 nanometers. So maybe 100 molecules over there. Now, like as soon as I start increasing my length cell, maybe I'm now talking about 100 nanometers, or maybe like 1 micron. So that is also very small scale in our day-to-day life, right? We are mostly what? How much can we see in our with our naked eye? 1 micron may be very like if you pay a lot of attention, maybe if something of 1 micron, maybe we can like identify it as a very small dot. Below that, it's very difficult to see. Even 1 micron is extremely small. I don't think it can be seen actually. Like maybe 100 microns can be seen like a small speck. Hmm. So. Uh, so this volume is still very small, but it is large when we are talking about molecules. So maybe like if we have 100 nanometer, if 100 nanometer is our length scale, then uh, there may be some billion or trillion molecules. Now, when we have so many molecules, this volume is fixed. This mass may not be varying that much. Hmm. So we are approaching a constant value. So if I plot something like this, hmm, so this is the density that I am measuring. So I am measuring how much mass is there and how much volume is there, and I am plotting this density with this length scale. So length scale is like the length of the cube. So if, for example, I am trying to calculate the density of in a cube, hmm, so this has length of L each side. So it has a volume of L cube, and I am trying to calculate how much mass is inside this cube, and dividing by L cube, I will get a density. Now, since the number of molecules is varying, when this length is extremely small, so when this length is extremely small, this density will vary a lot. Why? Because there are less number of molecules here, maybe only 5 or 6 molecules, and some molecules are constantly coming in and going out. So there will be huge fluctuation. So this density may sometimes we may get this high value, sometimes we may get very low value, sometimes in the middle, like something like this, but it is constantly varying. So we are not getting a stable number for this density. But as soon as we start increasing our length scale, as soon as we start making our box larger and larger, we will get more and more molecules inside, this box, and thus this density will slowly keep on converging to a value. So after a certain limit, after a certain threshold, this will gain a steady value. Hmm. So what is this? This is like the mean density, time average density, and this will get a stable value, and this is the region where we can actually consider my fluid as a continuous medium. Why? Because if I'm defining my properties at the this length scales, then if I move from one point to other, these statistical fluctuations will not disturb my calculations. Hmm. So that's when we can actually use our continuum hypothesis. So there are ways, very standard ways to identify whether my calculations can be done using this continuum assumption or not. Hmm. So that is basically the question. So the question is about the Knudsen number or Knudsen number, whatever you may call. Hmm. So Knudsen number, what is this? The definition of this Knudsen number. So this Knudsen number is used to uh, identify whether a problem can be solved using continuum hypothesis or not. Hmm. So if it is not solvable by continuum hypothesis, like if if it lies in this region, this particular region, then it will be solved using statistical mechanics, because there is a lot of statistical fluctuations in our system. So that needs to be taken into account. But after a certain amount of length scale is reached, we can use continuum mechanics. So this is quantified using this Knudsen number. So can you tell me how is the Knudsen number defined? So here two options are there for uh, definition of Knudsen number. So which one is true?
Sir, it's a ratio of molecular mean free path to characteristic length scale.
Yes,
Yeah.
that is correct. Hmm. So what is molecular mean free path?
Sir, the average distance between a molecule will travel before uh, in when molecules are in collision, the average distance between the two
Mhm.
molecules.
So, like molecules are are constantly like colliding with each other. So, the distance, basically the average distance a molecule is traveling before hitting another molecule. So, this is kind of like how many molecules are present in a volume. Hmm. So, if a large number of molecules are present in a small volume, they will undergo more collisions. Like like in a crowd of people, you like see the same thing. So if very small number of people are there in a very large ground, maybe they won't like they will travel a lot before colliding with someone. Hmm. But if more and more people are there, they will like travel. They will keep on colliding in very short distances. Hmm. So the concept is very similar of molecular mean free path. So it is basically the average distance before a collision. Hmm. And what is characteristic length scale? Characteristic length scale is basically the important length scale of the problem in hand. For example, you are studying a flow past a cylinder. So, if we are studying flow past a cylinder, what is your important length scale? This is the diameter. Hmm. So, this diameter of the cylinder you will consider as your important length scale. This is what is defining your flow. Hmm. If it is flow through a pipe, what is your important length scale? It is the diameter of the pipe. That is your important length scale. So, that is your characteristic length scale, the length scale in which your physics is defined. Hmm. So, if you are studying a flow of a river, then your river diameter you have to take into account. So, that is your large length scale. And if you are studying flow through pipes, that is also very large. So, then also you have to calculate pipe diameter. So, that will be a length scale. If you are studying flow through your blood veins and arteries, then the diameter of those arteries is your length scale. So that the these are very drastically different lengths that you may study fluid flow in, and due to this length, your physics will vary. So here, this Knudsen number Knudsen number is defined as this uh, mean free path divided by this characteristic landscape. And as you like would know and would understand, if this is very small, if Knudsen number is very small, that means like more number of molecules are there uh, in your small length scale, that you will a small amount of length that you may consider as a point in your system. So a lot of number of molecules are there, so no statistical variations will take place. So if this Knudsen number is small, then you are approaching towards continuum. You can take it as a continuous medium. If your Knudsen number is large, then you will not be able to take it as a continuous medium. So your A is correct. And what about option C? Problems with Knudsen number before zero point 0.1 can be evaluated using molecular approach, statistical mechanics. So is the first option true? First part of this true. Problems with Knudsen number below zero point 0.1 can be evaluated using molecular approach. Is this true? Hello.
So false, sir.
It is false. Why do you think it's false? Can you explain?
Because we use continuum hypothesis for
Yes,
below.
we definitely use continuum hypothesis, and continuum hypothesis will make our life easier, because otherwise, if we use molecular approach, what we are basically doing, we are solving for each and every fluid particle. So that will increase our effort to solve a problem. Hmm. But still, problems with Knudsen number 0.1 can be done using molecular approach, because molecular approach is always valid. What we do in molecular approach, we are solving Newton's laws of motion. We are solving Newton's laws of motion, but if the number of molecules are, let's say, trillion, or even more than that, in the order of Avogadro number, hmm, then the number of equations are ridiculously large. So not even a extremely high-end supercomputer can solve it in a reasonable time. So molecular approach will be very infeasible, but it will still be valid. It will be valid, but we will not use it. So if you are saying can be evaluated, so actually it is false. It cannot be, at least with today's computational capabilities. But theoretically, it is still valid. Okay, am I clear?
Yes, sir.
Okay. But what about the second part of this statement? Continuum hypothesis can be applied to find fluid motion for larger Knudsen numbers. This is false, right? That's what we discussed. For large Knudsen numbers, there will be statistical variations. And continuum hypothesis do not have the capability to identify those statistical variations. We will not be able to compute those statistical variations. Okay. So overall, this statement is false. All right. So yes, yeah, this is the solution given. So yeah, correct answer we have identified as A. We'll move to the next question. Okay, so here also is the same concept. So here an engineer is tasked with the analysis of a system where the length scale is 50 micron. So your length scale is given, while molecular mean free path is given as 100 nanometers. So this is also given. So here what the engineer has used, the engineer has used a classical boundary condition of no relative slip. So what is no slip condition? So no slip condition is if there is a wall, hmm, if there is a wall and there is a fluid, and the fluid will have some velocity. The wall may also have some velocity, but the relative at the interface between the fluid and the wall, the velocity will be zero. The velocity is zero exactly at the relative velocity between the wall and the fluid is zero. So when the wall moves, the fluid adjacent to the wall, just at the close of the wall, it also moves along with the wall. Okay. So that is your no relative slip condition. So he has used this and also obviously used continuum hypothesis. So can he use that? That is basically the question. So first what we will do, we will calculate the Knudsen number. So can you tell me what's the Knudsen number?
Lambda by L.
Yeah, lambda by L. Lambda is given here. What is the lambda?
100 nanometer.
100 nanometer is lambda. And what is the length scale? L?
50 micrometer.
Yeah. So can you calculate and tell me what is lambda by L? So this is 100 nanometers. Sorry, 100 nanometers. So 100 nanometer is 10 to the power minus 7, right? 1 nanometer is 10 to the power minus 9. 100 into 10 to the power minus 9 is 10 to the power minus 7. And this is 50 micron. 50 micron means 50 into 15 into 1 micron, that is 10 to the power minus 6. So I am writing this in meters to standardize the unit. So like if you solve this, how much this will be? This is 0.002, I think.
Yes, sir.
Yeah, 0.002. Okay. So is this very high or very low? Knudsen number?
Low.
It's low. It's definitely low. So we can definitely treat this as continuum. So first option is wrong since the flow domain can be treated as continuum. But okay. Uh, so both of these options say that this can be treated as continuum. Here it says this cannot be treated, so this option will not be there. And what about the no slip condition? So no slip condition, we also use a very standard rule here. So this is like very small Knudsen number. So no slip conditions can be used here. But if like the Knudsen number is say for example 0.1. So 0.1 is less than 1. So Knudsen number is small. So continuum may be used. At least for water it is generally used. If it is like zero point 0.1, it can be used. But this no slip cannot be used because no slip also there is like interactions between the wall that are not really well captured if you simply use it a relative no slip. So if the molecular mean free path is large enough, that such slip effects in the wall may affect the flow dynamics, then we have to use some model to account for the slip between the wall. So if there are less number of people, so for example, like you can always think of it in terms of a crowd. So that is a very good analogy. So for example, there is a lot of crowd in some ground. So near the walls, there will be people who won't be able to go forward because of this wall here. So they are like no slip. But if there are less people, then there will be motion along the wall as well. So like for example, in a narrow hallway, some people are passing. So along the edges, you will see the people are getting stuck because like there is no place to go. But in the middle, there is flow. Hmm. But if there are less number of people, then everyone is traveling. The people along the edge are also traveling, and in the middle also they are traveling. So in same thing here also at an intermediate Knudsen number, the no slip condition is not valid because there is some motion along the wall as well. But that is mostly taken in this point 0.1 range. But this is very small. This Knudsen number is very small, so it very safely notes this no slip condition also can be applied. So he is right. So he is right. The flow domain can be treated as continuum, and no slip can be applied. Okay. So if you have any question regarding this Knudsen number and when we can take continuum and when we need to use other methods and anything about the other methods, then you may ask me. So this is like interaction only, so you may speak up and ask. There is no problem. Okay. So you may speak up and talk if you have any doubts. Otherwise, I will proceed to the next part. And like any doubt regarding this section, you may ask me. And like in the next sessions, we will move to the next assignment. So like I guess when you have to submit means assignment 2, maybe you have to submit right now, but assignment 2 problems will be discussed in the next week. Okay. All right. So this is the solution that is provided. So here also they are saying like it is saying this thing. So in this range, this is known as the slip flow region, in which no slip condition becomes invalid, although continuum can be still be used. So what we do is basically along the wall we define some slip velocity or something known as a slip length, which you may study in later part of the course. So that is used to add uh, to like define the slip along the wall. Otherwise, a no slip can be used if your Knudsen number is very small. Okay. So in the next question, let's come to the next question. So uh, yeah. Here we are discussing about two very important things. It is a system and a control volume. So can you tell me what is a system and a control volume? Basically, the question is this only: the definition of system and control volume. You may like answer that one. What is the control volume? You must have in the lectures it must have been discussed. Something you may say.
Sir, in system, there is only energy transfer, no mass transfer.
No mass transfer, right? Yeah. So the system is basically defined in terms of mass, or you may say like since we are discussing fluid mechanics, so in terms of fluid particles, so a collection of particles, so those are only contain the particles contain the mass, so collection of particles can be described as a system. And if the particles move, the system is moving. If the particles, those collection of particles are deforming in some way, then the system is also deforming. So we follow, if we are using a system for our analysis, we follow those group of particles. And here this system, this option is saying the system is defined as a fixed identifiable quantity of mass. So yeah, so fixed identifiable quantity of mass, and the system boundaries separate the system from the surroundings. Boundaries of the system may be fixed or movable. Like I said, like if it is a group of particles, so it may definitely move. When the particles are moving, it will move. However, no mass crosses the system. So, like you said, so there is no mass transfer along the boundaries of a system. Hmm. However, energy transfer can definitely take place. So, this option is correct. And what about control volume? Control volume is not about mass. Control volume is a geometrical space. So here it is very well written, geometric boundary. So this is control volume. So like we define some space. Let's say your room. Hmm. In your room, some person may come, they may go. Like you might be sitting here, and your friends come over. So number of particles inside this control volume increases. Then they leave. So the number of particles may decrease. There may also be energy transfer. Hmm. But what we are doing is basically we are observing the same geometrical space. So we are observing the same geometrical space. And whatever is happening in this geometrical space, whatever mass transfer and energy transfer is happening, we are taking all those things into account. And this approach actually simplifies a lot of things, especially if we are using continuum mechanics. So as we are already considering fluid as a continuous medium, we will just like look at a particular section, a geometrical section, and we will just observe whatever fluid is coming in and going out. Hmm. So this is also known as Eulerian approach. I think you may have heard about this as well. So this is known as Eulerian approach. I am not sure about this. Eulerian. And what is the other thing? Like if we are using a system, what is it called? It's called a Lagrangian approach. So if we are using a system, if we are following a bunch of particles, then that's called a Lagrangian approach. This is basically approaches used to solve fluid mechanics problems. So both of these statements are correct. So this option C is the correct one. Both of A and B are correct. Okay. All right. So now we come to pressure and stress. So this is a very important concept to understand in fluid mechanics. It is the pressure and stress. Pressure, there are two types of pressure. What are they? One is mechanical pressure and another is thermodynamic pressure. So can someone tell me about them? What is mechanical pressure? What is thermodynamic pressure? If you have any doubt, you may ask me. And like if you have some particular problem to discuss, like at the end of the session, also we can discuss about it. Okay. Yeah. Can you please um, try to answer this?
Sir, mechanical pressure is basically the force acting per unit area, and the thermodynamic pressure is the force which we exert on the system. Like for an piston cylinder, we the force we exerted.
Okay, but you said force in both those statements. So how is it different? So force we exert, like on the piston, for example. So that is also like force per unit area only, like you define as pressure there as well, right? So how is it different from like mechanical pressure? That is also mechanical pressure, right? You can interact. No, there's no problem. Like, hello, he was
Yes,
angry.
sir.
I think. Yeah. Okay. Hmm. So you are telling mechanical pressure. You are telling correctly. So what is mechanical pressure? Mechanical pressure is like, for example, if I just isolate some volume, isolate a volume of fluid. Okay. Hmm. Uh, are you the only one here? You are the only one here, right? So you can interact now. You can keep your mic open. Hmm. Yeah. So if you take a small volume of fluid, then whatever is the normal force per unit area, that is your pressure. That is what mechanical pressure, because this is the mechanical force we are talking. And what is thermodynamic pressure? Pressure you have come across another in another place in another topic, that is thermodynamics, right? Where you what you have discussed like uh, means equation of state. You have discussed relation between pressure and temperature using like specific volume, or density. You have uh, definitely used some relation like this, right? P
Yes,
v
sir.
is
P
equal
is
to
equals to
nRT.
1 RPM.
Hmm. So what is this? P is pressure here.
Yes, sir.
This P
Yes,
is
yes.
thermodynamic pressure. Okay. So this P and this force per unit area pressure, they must be related in some way, right? So this is the relation that we are really concerned about in fluid mechanics. So when we are talking about mechanical pressure and when we are talking about thermodynamic pressure, so they are related in a very special case. So let's first means there are multiple questions I think regarding this topic itself. So let's see what this question is asking. So consider the below expression regarding pressure and normal stress components acting on the fluid element. Hmm. So what are these? These are stress components, right?
Yes, sir.
These are stress components, and it is written XX. What does this mean? Sigma XX. What does this mean?
Sir, on X direction and situated on plane X.
Hmm. So x direction and on plane x. So like if I have a fluid element, something like this, and if I have the directions also like this, so this is for example the x direction. So I am talking about this plane. I am talking about this plane. So the first x denotes that. Second x is the force direction, is the stress, like force per unit area is the stress. So the this direction is also towards the x. Hmm. Similarly, YY is normal and ZZ is also normal. So this is minus sigma xx plus sigma YY plus sigma ZZ divided by 3. So this is basically the average normal stress, right? Whatever the normal stresses we are getting, we are just averaging. Hmm. So what is this? Is this mechanical pressure or thermodynamic pressure?
It's a mechanical pressure.
This is mechanical pressure. Why? Because this is simply talking about force per unit area, nothing else. It is talking about normal force from all three directions. We are just averaging it, and like uh, we are finding out average compressive force per unit area on a small fluid area. So this is mechanical pressure. Okay. Uh, so indicated pressure is called mechanical pressure and is in general different from thermodynamic pressure. So this option is correct. Let's check if others are wrong. Indicated pressure is thermodynamic pressure, so this is wrong. This indicated pressure is not thermodynamic pressure. Thermodynamic pressure is something that we get from here, hmm, using our thermodynamic equation. So this is not the case. And indicated pressure is an invariant quantity. That is, it does not depend on the coordinate system used. Now, this is a very interesting question. So, do you understand this question first of all? What this third option is?
Sir, invariant quantity means the quantity which does not depend on the orientation, I mean theta. So,
What is
but
theta?
uh, the angle at which the stress is applied.
Okay, okay.
But
So
this is dependent on.
how does it depend?
Uh, because sir, if we change the angle, maybe the stress may be different.
Definitely, the stress will be different. So if I change the angle, so for example, in the fluid element, hmm, so if I am like, I am worried about, for example, some plane like this. This is situated at some angle. So like the object is like this, and some angle I am talking about. I'm not talking about my general x and y direction. So definitely that will be different. But here, what we are doing, we are already defining three directions, right? We are defining x, we are defining y, we are using z. We are using all the three directions, then averaging. So is this dependent?
No, sir, it's not dependent.
Because all three directions we are using, right? So
Yes,
this is
yes.
not dependent. And this also actually you like we last day discussed about mathematics, right? We were discussing about matrices. We were discussing about eigenvalues, eigenvectors, and all. So this is actually very related to your eigenvalues. So, like, if you have means very clear picture of what are eigenvalues, you will actually see that this sum, this thing, this is nothing but summation of your eigenvalues. So, what is this? Whenever you have stress and you are given three axes, you can, this is your stress tensor. You can write your stress tensor like this, sigma xx, hmm, sigma yy, sigma zz, and your other terms also here you will write. Your other terms you will write. So what is sigma xx plus sigma yy plus sigma zz? This is the sum of the elements of the diagonal, right?
Yes, sir.
This is also known as trace. Hmm. This is just another term. So what is this basically? This is basically your summation of your eigenvalues. Hmm. This is summation of eigenvalues, and this does not depends on your x, y, and z direction. For example, your x and y direction are like this. You can see my video as well, right?
Yes, sir.
Yeah. So if my like x, y, and z direction is like this, now if I rotate, my sigma xx will change because my x direction is now this, not this. So my sigma xx will change, sigma yy will change. But this summation will stay constant. This is a stress. This is a property of a matrix. Even if I rotate, if I do a rotational operation on this, this value trace will not change. So this is actually an invariant quantity. This is called an invariant quantity. The stress is an invariant quantity. So pressure also, since this trace of a matrix is an invariant quantity, so borrowing from that, pressure is also an invariant quantity. Okay. So this option is actually also correct. So
Yes, sir.
this option is correct. So both A and C are correct. So your final answer will be D because both A and C are correct. Okay. Well, I will move to the next question, but like let me ask you, like what are you currently doing? Are you an undergraduate student or like doing masters or means
No, sir. I'm an
working
undergraduate student, third year.
third year undergraduate student? Okay.
Yes, sir.
Which college?
Sir, I'm from Odisha, Bir Sundar.
Okay. Okay. So on undergraduate third year. So you have fluid mechanics in your course right now.
Yes, sir. Now, right now in this semester we have fluid mechanics.
Okay. All right. So these things will be very useful for you. Uh, yeah. So correct answer is D as we discussed. So this is basically definition of your mechanical pressure. So this is definition of mechanical pressure. Or we can write this as PM because we will use P for both, like thermodynamic also we may use or mechanical also we may use. So mechanical we can simply differentiate using writing as subscript M. Okay, we'll move to the next question. So next question is also very much related to what we discussed right now. So uh, here they have decomposed stress into two components. So first, let me talk about that. So the stress may be written like this. This is a tensor quantity, so this may be written like this. Another way to write stress, another way to write stress is also using index notation. Have you studied index notation? Have you studied index notation?
Yes, sir.
Yeah.
Sigma ij.
Hmm. So sigma ij is basically like it is representing what, a second order tensor, right?
Yes, sir.
If I put I is equal to 1, j is equal to 1, then it is like my sigma xx. It is a particular direction. It is specifying the stress in a particular direction. It is basically a component. Hmm. Uh, we can also represent like the vectors. For example, velocity vector as vi. So we have three components: v1, v2, v3. So we are simply not writing each component separately. We are writing it at one place like vi. So if I just simply replace I as 1 or 2 or 3, I will get three different equations. So instead of writing these three equations separately, I'm using a shortcut and I'm replacing these numbers using I, and I will just say that this I may be 1, 2, or 3. So whatever the case might be, I'll put it and I will get different equations. Now when I have I and j, my I also may be 1, 2, and 3. My j also may be 1, 2, and 3. So how many components will I have? I will have 9 components because this is 3 into 3, 9. So I like I may have 3 values, j may have 3 values, so total 9 values. So this is divided into two terms. One is minus p delta ij. I will come to this delta later, and another term is tau I. So can you tell me what is delta ij? Do you know what is delta ij? Delta ij is very like means defined, well defined matrix. So delta ij is basically this 1, 1, 1, and rest are 0. This is also known as identity matrix.
Identity
If you
matrix. Yes.
write it in a matrix form, if you write it in ij form, the index form, this is known as Kronecker delta. Kronecker delta. Very a speciality about this also is what is this stress? We just discussed stress, right? Stress is sum of the diagonal elements. So diagonal elements sum is 3. So and also determinant is 1. So these things are there. So these are the stuff which actually do not vary if I change my rotate my x, y, and z. So whatever rotation I may have, these values remain the same. So Kronecker delta has a very special property that whatever direction you rotate, it will always be this 1, 0, 0, 0, 1, 0, 0, 0, 1. When I write it in the matrix form, I am actually writing components, right? I'm writing the components based on where my x, y, and z are defined. So if I rotate, the components should change ideally. But Kronecker delta has a special property, like whichever direction you decompose it at, you will still get this identity matrix. So here, this p, is actually uh, thermodynamic pressure. Okay. So like I'm just stating it here. But like it can be argued and we can arrive here from or rather from here we can arrive at whatever arguments we use in thermodynamics. But like that is cannot be discussed right now. We can discuss it at an advanced level. So this here, this P is thermodynamic pressure, and this tau is Ij is another component of stress which is different from this thermodynamic pressure. So what does this thermodynamic pressure do? Thermodynamic pressure means has a relation with the temperature and specific volume. So it has a relation with the state of the matter and like the physical state equations. This variable is used. So here also in the momentum equation we use the same variable, so that in any case we are solving this along with our thermodynamic equations. Then this is very like the variable is already defined. Hmm. And the rest of the component is taken in this tau ij. So this is also called as deviatory stress tensor. Hmm. So this is the other component of the like stress. Apart from thermodynamic pressure, we also have deviatory stress. Now we come to the question. Hmm. So here they have defined, they have done exactly that. What they have done, this is your sigma ij, and this they have broken down into this minus p delta ij. Hmm. And this is tau ij. Okay. Yeah. So they have asked this, like they have given two statements, and they have asked which one is correct, which one is wrong, or if both are correct or both are wrong. So option one is, when dealing with incompressible flows, fluid pressure variable P is always interpreted as mechanical pressure. Is this correct?
No, sir. It can be as thermodynamic pressure. It can be also introduced.
Yeah. So it turned out to be thermodynamic pressure. Hmm. But it has a very specific condition here, that is incompressible fluid flow. Hmm. So incompressible fluid flow, this mm, what we have here is from tau ij we do not have any component which like means uh, fulfills this condition. So basically here we come back to the equation. We come back to this equation. Hmm. So here tau ij, deviatory stress tensor, tau ij, this also is this is dependent on your velocity. This is dependent on your velocity. Hmm. So have this been discussed in the class? It should be, right? This is week one assignment, I guess. No.
Yes, sir.
Yeah, this is discussed in the class. So hopefully I'm not stressing too much. Hmm. So tau ij is dependent on your velocity field. Hmm. So this is dependent on your velocity field. It has two components. One is your Newton viscosity component. Mu is your viscosity, right? The dynamic viscosity. Hmm. So this into, this is written as del ui del j del xj plus del uj del xi. So here you see I and j are here reversed. Hmm. So basically, when you have like x component velocity, then in the, like for example, if I take ux, then the derivative will either have u y or z, not x. Hmm. So this is basically like x direction velocity you are having, and you are moving in the y direction to see how much the x direction velocity is. So this is like a shears. Hmm. So this is basically shear component. So this viscosity is Newton's viscosity or shear viscosity, whatever you call. Hmm. So this is one component, and another component is there, which is like defined like this. Hmm. Del x this. So what is this? This is same as this. Hmm. When we have repeating indexes, you know what we like what we do, right? When we have repeating indexes, we just add them up, right? Repeating indexes add up. Hmm.
Yes, sir.
Hmm. So del uk del xk, this is nothing but del u1 del x1, or I'm just writing del ux del x plus del uy del y plus del uz del z. Now from your vectors, you also know that this is basically nothing but divergence. Hmm. Now, what is there it is asking for incompressible flow. The incompressible flow, what happens to divergence? Divergence is 0, right? This
Yes,
is
sir.
equal to 0. So divergence is 0 means this term is not there. So only this portion is there in your incompressible flow, right?
Yes, sir.
So if that is the case, then like your normal stresses, however you are defining this mechanical pressure, you are defining using your normal stresses, right? Sigma xx, sigma yy, sigma zz. If you do that same thing here, tau xx plus tau yy plus tau zz, you will see that you will see you'll only get this pressure here P. So here is sigma xx plus sigma yy plus sigma zz will have this pressure component. So if you like try to solve for this, do this exercise, okay? Like at least after this class, you should do this exercise. So minus sigma xx plus sigma yy plus sigma zz. So here what you have, sigma xx is this whole thing will have P plus whatever is the component from this side. And after this, try and do this. And if you cannot, then please let me know in the next week session that you are facing here. Then I will before starting only I will discuss this first. Then I will move on now to the next week's topic. So this term should come out to be 0. Okay, the second term should be 0. So here, if this is incompressible, if del ux del xk is 0, this portion is 0, then you must have this thing as your P. So only in case of this incompressible flow, this P will always be will also be interpreted as Pm. This is also thermodynamic pressure, by the way. Definitely, this is thermodynamic pressure. That's what we discussed first. At first, we discussed this. Then we discussed this. So here, P is also thermodynamic pressure. Here, the mechanical and thermodynamic part will be same. Okay. Okay. Do this exercise, then it will be more clear to you. This just calculate minus sigma xx plus sigma yy plus sigma zz by 3. This thing you will calculate, you will find the answer is P if your this divergence is 0, if this portion is 0. Okay, so this is actually true. This is true. For compressible flow field, pressure is thermodynamic pressure, but mean normal stress is felt on surfaces of a fluid element that is not necessarily same as P. What is mean normal stress? Mean normal stress is nothing but this minus sigma xx plus sigma yy plus sigma
No,
zz
yes,
by
sir.
3.
Yes, sir.
What mean normal stress is nothing but mechanical pressure, right? This is mean normal stress is mechanical pressure. So and this pressure P is thermodynamic pressure. So this is true. This first part is true. Mean normal stress that is mechanical pressure. So I will write here PM felt on the surface of is not same as P. So PM is not equal to P. That's what they are saying. So here they have also explained it. So pressure variable P and PM, these two are not necessarily same. So this is also true
True.
because of this term, because uh, only because of this term, this lambda del uk del xk. So this is not 0 for your compressible flow field. So whenever you are calculating this your this minus sigma xx sigma yy sigma zz by 3, you will also get this lambda term. And this whenever this portion is del uk del xk, this is going to 0, then your mechanical pressure and your thermodynamic pressure is becoming equal. So here, yeah, here the same thing is explained. So here the explanation is given. So where is it? Yeah. So this is called your viscous stress sensor or your deviatory stress sensor that we discussed. Hmm. Now for incompressible fluid, someone is there. Let me name. So for your incompressible fluid flow, your pressure variable is always interpreted as your mechanical pressure. Hmm. Because this term, this uh, delta UK del UK del XK, this is going to 0. That's why your pressure here will be equal to PM. However, for compressible flow fields, this divergence of the velocity is not 0. So your normal stresses will have additional component other than your thermodynamic pressure. So your mechanical pressure, that is the normal mean normal stress, will have additional component other than your thermodynamic pressure. So those two will be different. Hmm. So here, how they are different is calculated. You will also, like if you calculate, you will also get a similar result. So here, your divergence is here. So this divergence term, if it is 0, then these two are equal. If they are not 0, if the divergence is not 0, if it is compressible flow field, then these two are not equal. Hmm. And also sometimes this for some fluids or some cases, this term is also sometimes taken as 0. So this is called the Stokes hypothesis. If this is 0, lambda plus 2 by 3 mu. If this is 0, this is called the Stokes hypothesis. So if Stokes hypothesis is valid, then also your thermodynamic pressure will be same as your mechanical pressure.
Mechanical pressure.
Okay. Hmm. So two cases there. All right. So yeah, next you have some numerical problems. So have you already done this numerical problem?
So this question was not there in the assignment.
This question was not there in the assignment. Okay,
Yes, sir.
okay. So yeah, then you do this. This should be pretty simple. So I think some few people have joined right now. So we are currently solving the assignment one, which is after your week one. So if you have any questions or doubt regarding the this assignment, you may ask. We are currently in the question six. So we have already covered the till question five. So this first five questions we have covered. If you have any, we have discussed the Knudsen number, and we have also discussed about your pressure, thermodynamic and mechanical pressure, and calculating stress components. So we are currently doing we are calculating stress components. So if you have any doubt regarding these topics, then you can ask. So what we will do here? How can we calculate the traction vector? So this is dot product, right? We'll take the dot product. You may, yeah, you may use this symbol, you may use other symbols as well. So I prefer this one. You have to take the dot product. So let me do it with you. So this the components are given here. So I'll write down the components. So this is basically a matrix multiplication. So 50, 10, 30. And your normal vector is given here. So 0.4, 0.6, 0.693. Can you tell me the first component? How much that this will be? You must speak up.
Sir, 46.7. Yes, sir, 46.7 I can.
46.7. Okay. So this is 46.7. So this is, yeah, 20 plus 6 plus about, yeah, about 20. So this will be something like this. Yeah. Okay. Next one. Next component.
Sir, 74.8 J cap.
74.8. Okay.
Yes, sir. Yes, sir.
What about the last one?
So it is coming different is 136.2 J cap.
Okay. So the last one is 0.4 into 30, which is 12.
Yes.
12 plus 0.6 into 20. So that is also 12 plus 15 into 0.693, right? So this is, you can like simplify whatever way you like calculating. So what I will do is like 6.93 into 1.5. So this is like 1.5 times will be around 10 point something. So here the option is like 12, 12 is 24 plus 10 point something, so it will
34.
be
34.
34.
Yes.
Okay, you can do precise calculation with your calculator. I don't have a
Yes, sir.
calculator right now. Yeah, so mm, this is your correct answer. Yeah, this matches. Okay, so what we just did that we did something, but we must also understand what we did, right? So, for example, like what we have is we have stress at some point here. Stress at some point is given. Hmm. So why I'm saying point, because this is basically we define these things in our continuum hypothesis, and for a point it is defined. We might have used cubes for describing what is stress, or like even like tetrahedrons for like calculating traction vectors and all. But what we always assume is that these tetrahedrons and these cubes are very small, so it's almost like a point. Hmm. So stress is defined as a function of space. So we are looking into some volume, like control volume, and we are identifying some point which have some XYZ coordinate maybe. Or like if I want to write like this, I can write like this. If I want to write like this, then also I can write like this. Or so it is basically a function of your this point x. And so a stress at a point is given. Some coordinate axis is defined, and for using that coordinate axis definition, this x, y, z, whatever coordinate axis definition, this stress component, this stress is divided into your components. So your ith may be the direction of whichever face. So for this small point, whichever face you want to, this point it is also like maybe a small cube. So whichever face is this pointing at, so this might be your first this first dimension, and your j dimension will be the force acting. So if your first dimension, like if it is 1 x axis, and your like second thing is 2, so this is like a shear stress in your x plane. So like that, some components are defined of sigma 1 1, sigma 1 2, and so on. So this is defined. Now what I want to find is actually traction vector. So traction vector, what is it? We will take a particular phase and we will find the resultant force acting on that particular phase, force per unit area acting on that particular phase. So I will what I am doing is I'm taking this point, and I'm taking some direction, some normal direction, this direction. And what I want to say is, if a very small area is defined around this point, then what is the force acting on this? So is it clear? How did I get this area? I got this area using this normal vector. So I have a normal vector given, and whatever plane is this is normal to that particular plane is this plane, and I am trying to find out what is the force acting per unit area on this plane. So that is my traction vector. That is my traction vector. Okay, so this may have XYZ components. This may not be your normal to this uh, uh, particular direction. This may be oriented anyway. Okay, is that clear? Is that definition clear?
Yes, sir.
Okay, so we got our traction vector. Now, what is the next question saying? Next question is saying to use this, use the previous question. So we use the stress tensor and the surface unit normal from the previous problem and find out the normal stress. So what will be the normal stress? The normal stress is like this point we have got. We have got a normal direction. We have calculated our traction vector. What will be the normal stress? Normal stress will be basically the component along this normal direction. This component along your normal direction, whatever you may call it, some TN, or like the normal stress, and there will be another component which is the shear component, which will be the shear stress. So you may call it TS or tau, whatever notation you may want to use. So what is asked here? We are asked the normal stress. So what you have to do, basically find the component of this traction vector with respect to this normal. You can do that. So what was the traction vector? Traction vector is this 46. You can see from here. We have both traction vector and the normal vector. Normal vector is 0.4i, 0.6j, and 0.693 kk. And you have to find this.
So 87.36 megapascal.
So this is 87 point.
368 megapascal.
So you're close to this. Is it
Yes,
close
yes.
to this? Okay. Hmm, okay. Yeah. Hmm. It's pretty simple. Just zero point 0.4 into dot product. Zero point 0.4 into this into this. Just add them up. Hmm, okay. Good. Okay. So this is our last question. I guess this is our last question. Yeah. So here also some concepts are given. This is also related to your pressure and stress. This is very important. Hmm. Uh, so, so let me read this question. Pressure stresses and viscous stresses are two different concepts often discussed in relation to fluid mechanics problems. When the fluid is at rest, which among the following statements is true? So we have to identify whether some statement is true or false. We will like take each statement and discuss about them. So first is when the fluid is at rest, only stress which is acting at any surface of any fluid element is the local hydrostatic pressure P, which acts inwards and normal to the surface. So few things are mentioned here. The fluid is at rest. Hmm. So we have no velocity. So the whichever reference frame we are looking from, the fluid velocity is zero everywhere. That means the fluid is at rest. So the statement they have made is only stress acting on any surface of any fluid element is local hydrostatic pressure P. Hmm. So hydrostatic pressure is mechanical pressure. So they are saying the only stress acting. So basically sigma ij. If I break down this into components, the only thing that is acting is hydrostatic pressure or the mechanical pressure. So I will let Pm. So Pm minus Pm minus Pm. So the whole stress tensor becomes like this. So that is the statement. We have to judge whether this is true or false. And this is always acts inward and normal to the surface. This minus sign I have already put here. So like, the minus sign indicates it is inward. So can you tell me whether this is true or false?
Sir, the first statement is true. Yes, sir. At rest, the only static force, hydrostatic force is acting at
Hmm.
rest.
Hmm. Okay.
But the second statement, which always acts inward and normal to the surface, this may be false.
Okay. Why?
Yes, sir. It's also the normal stress also acting. No, sir.
Normal stress is acting, but means what this the second part. What does it? What is it saying? It is saying that which always acts inward and normal to the surface. So which are you opposing? Are you opposing inward or are you opposing normal? Which is not true.
No, sir. The second statement, B statement is false. First one is
Oh,
true. A is true.
A is true. Okay, okay. So okay, I was just discussing about it. All right. So you are saying, okay, B is basically the same thing, but they have said that it may act inward or outward, any of the directions it may act. That's what you are saying, no? This is false.
Yes. Yes,
Hmm.
sir.
So it will not act outward. That is correct. You're absolutely right. It will always act inward because like the pressure is positive, and you're like if this is true, if this is true, then definitely your stresses are acting inwards. But is this true? So this is also true. This is also true. So we have already discussed like sigma ij. The stress has two components. One is the pressure component. This is the thermodynamic pressure if I am writing in a very general way. And another is deviatory stress. Now this deviatory stress is a function of velocity. So this is a function of velocity. Now, if my velocity is zero, this is zero. Because all of the terms here are basically gradients of velocity. So I already have this. And what is my mechanical pressure defined as? Mechanical pressure is defined as is sigma xx plus sigma yy plus sigma zz by 3. This is how my mechanical pressure is defined. So if I put it here, I will see my P, my thermodynamic pressure is equal to mechanical pressure. So basically sigma ij is equal to minus P delta ij. So when my fluid is at rest, only stress that is acting is my local hydrostatic pressure P or the mechanical pressure P. Other stress components are zero. Okay, and it is acting inward. So A is correct, B is false, B is not correct. For a fluid at rest, the stress tensor reduces to this, and hydrostatic pressure P in the above equation is same as the thermodynamic pressure, which we are familiar with from our study of thermodynamics. So, is this true? Is this statement true? So, fluid at rest, they are saying that this stress tensor may be written as this: sigma ij is equal to minus P delta ij, where P is thermodynamic pressure. So, is this statement true?
Yes, sir. Both the
This is true. We just saw that here in this case, if fluid is at rest, my both the pressures are equal. Thermodynamic and mechanical pressures are equal. So this is also thermodynamic pressure, and this is also mechanical pressure. So this is also true. So both A and C are correct. This is my correct option. Okay. So I guess you have a clear understanding now of what is mechanical pressure, what is thermodynamic pressure, and when they are equal and when they are not equal. So if I uh, if if it is an incompressible flow, this statement is valid. If this is valid, or if my Stokes hypothesis is valid, this this is valid. If any of these two are valid, then my this is confirmed. Otherwise, these two values may be different. Depending on the case, these two values may be different in other cases. And whenever these two conditions are satisfied for fluid at rest, U is zero. So this first condition is definitely satisfied. So in that case, your thermodynamic pressure is mechanical pressure. If Stokes hypothesis is valid, your thermodynamic pressure becomes equal to mechanical pressure. Otherwise, these two may be different. What is mechanical pressure again? Mechanical pressure is the mean normal stress. So mechanical pressure is defined as this minus this sigma kk by 3. So kk, you understand, is just summation of the normal diagonal
yes.
terms. So this is your mechanical pressure. What is this? This is basically the definition that we use. We use it in PV is equal to nRT. We also use in our stress definition. So P delta Ij, this P that we are using, plus tau Ij. So this is my stress. So this P that we are using, this is my thermodynamic pressure. Okay. So this you have to keep in mind. All right. Yeah. So the same thing is explained here. Yeah. So here we end today's assignment solving. So if you have any questions, then like you feel free to ask. Okay. Do you have anything to ask?
No, sir. Sir,
Okay.
one thing
Yeah. Yeah.
that In assignment questions and the questions which we are doing right now, it's very different, sir.
Is it okay? Yeah, I have been sent these assignments by the NPTEL teams.
Yes, sir. I mean,
So
they're basically.
if you have any like doubt regarding the assignment questions that they have given, you we may discuss with that as well. Okay.
No, sir. I mean, well, all the questions are I'm covering the concepts very well, but they're very
Okay.
different. They're helping
Oh,
on
sure.
assignment questions as well. Yes, sir.
Okay. Yeah. I guess then yeah the because since you have to submit those assignments, maybe they have kept it different. I don't know why
Yes,
they
sir.
have kept it different. But I hope like this is helping you solve this.
Yes, sir.
Well, thank you. And you are getting your the links, right? You are getting
Yes,
the
sir.
link.
Yes, sir.
Okay.
We are getting the
Okay.
links on. Yes.
Mm. Okay. Thanks.
Thank you, sir.
I'm ending the session right
Yes, sir. Thank you, sir.
now. Okay.